It's Tuesday, November 9th. My name's Juan Brown. You're watching the Blanco Lirio channel. And through secondhand knowledge, after talking to somebody that has spoken with the captain involved in the MD-87 accident that occurred on 19 October in Houston, Texas, we're going to take a deep dive into DC-9 flight control systems today, as that is where investigators are going to be looking for the cause of this accident. According to somebody who spoke to the captain, that captain went roaring down the runway there at Houston, Texas. V1 went to rotate, and just as eyewitnesses reported, the aircraft never rotated. The nose never came up. This forced the captain into a late reject decision on a short runway, some 6,600 feet long or so, forcing him to reject the takeoff and take the aircraft off the end of the runway. Fortunately, everybody survived. Also, according to the initial reports from the captain, it sounds like he did hit the thrust reversers. He got the buckets out and then instinctively retracted the buckets once the dust settled. So let's go inside where it's a little bit warmer and do a deep dive DC-9 systems review on flight controls, particularly the elevator on the DC-9, and take a look at what investigators are going to be looking at and some prior history with this model of aircraft. Here at the Blanco Lirio World Global Headquarters, we got another 1 3/4 inches of rain on the rain gauge from this storm. We had 1.5 inches from the previous couple of storms, plus the 18 inches of rain from the first whopper storm this month of October, giving us more rain so far in this month of October-November time frame than we've had all year last year, giving us a good start on recovering from this rain deficit and refilling the critically low reservoirs here in Northern California. This is the part of the aircraft that investigators are going to be focusing their investigation on, and fortunately, the tail section of this aircraft survived very well intact. November 987 Alpha Kilo. This aircraft was operated by a professional contract air crew, but that contract only provides the air crew for this aircraft and does not provide the maintenance to this aircraft, and I do not know at this time who does the maintenance on this aircraft. Now let's go over some of the components of the tail of this aircraft while we're looking at this picture, and we'll get into further detail. I remember when I flew the MD-80, it's a tab-flown aircraft, and as such, it's a elegant, simple aerodynamic design, and I do vaguely remember the flying characteristics of the aircraft giving it kind of a wallowy feel to it as you operated the tabs, which operate in turn the control surfaces while flying the airplane, especially on final at slower airspeeds. So looking at the tail here on the accident aircraft, this surface here is, of course, the horizontal stabilizer, and this is where you get your pitch trim for the MD-80 through a jack screw bolted to the leading edge of this horizontal stabilizer. I don't believe that was a problem in this particular accident, though it has been a problem before. Referenced the Alaska accident off the coast of Southern California years ago. This surface here is the elevator, and it is a free-floating elevator. In fact, they're separate left and right. Only aerodynamic loads move this elevator. Otherwise, it's a free-floating elevator. You see these tabs here on the back of the elevator? This is the control tab. The inboard tabs, these are the control tabs. This is the only portion which you mechanically move with the yoke of the aircraft in the DC-9. These other two tabs, the middle one and the outboard one on each side of the elevator, are the servo tabs. They are connected to the elevator and move in relation with the elevator to assist you when you move the control tabs. The control tabs are also hydraulically assisted with the number 1 hydraulic system, but you can still fly the aircraft just fine without that hydraulic pressure, and that's part of the beauty of the simplicity of this design. Here's a closer look at the flight control surfaces on the tail of the DC-9. A is the horizontal stabilizer, which is trimmable via a jack screw on the leading edge. This is, by the way, is looking aft. Here's the tail of the aircraft. B is the elevator. D is the inboard control tabs, again, the only part that you move as a pilot. And C, here and here, are the geared tabs, or I call them geared servo tabs. which assist the control tabs in moving the elevator aerodynamically, which simply free floats. Here's a detailed look of the DC-9 elevator control system. Here's the yoke, and control cables go all the way back to the control tabs located on the inboard section of the elevator, and they are hydraulically assisted here by the number 1 hydraulic system and can be overridden in the event that there's a hydraulic system failure or a jam in the hydraulic system. So again, the pilot is only moving the control tabs here on the inboard section. Geared tabs are simply bolted to the horizontal stabilizer, rear spar. One of the problems with the DC-9 design is the tail is so high up in the air that it's very hard to service. You can't get to it for a pre-flight inspection. And also, how do you put gust locks on a tail that's so high up off the ground? Well, built into the DC-9 are these elevator viscous dampers located right here. A viscous damper is common in a lot of different engineering applications to stop things from banging around suddenly, stop rapid movements of mechanical systems, in this case from the wind from banging the elevators around while it's parked on the ramp. These viscous dampers are good for up to about 60 knots of wind speed, or at least they were originally on the DC-9. Another catch with this system is when you go to do a flight control check, you can move the yoke and move the control tabs, and it feels to you like everything's working just fine. But this elevator may be jammed or fixing to jam, as they say, about to jam up, and yet your elevator control feels just fine. And if you were doing a pre-flight inspection of the aircraft, moving the yoke, all you're going to see is the control tabs move. You're not going to see the whole elevator move until you have aerodynamic forces over that elevator, like when the aircraft is flying. This video clip comes to us courtesy of Just Planes, the world's largest aviation website or YouTube channel on YouTube. This is an old clip of a MD-80 doing what used to be called a blowback maneuver, where he would use the reverse thrust to pull himself away from the gate instead of getting a tug to push him away from the gate back when gas was cheap. But what I want you to look at is the elevator during this blowback maneuver and note how it splits. See the control tab? There come the reverse thrust buckets. The aircraft begins moving back into the wind, and the wind pushes. See how that elevator splits like that? The elevator on the DC-9 is not mechanically connected. It only free floats in the wind, aerodynamic loads. The only thing that moves, that controls the elevator on the DC-9 is these control tabs, here and here. The rest of it free floats. Now, those of you in the comment section that said this Houston accident sure sounds like the Ameristar charter flight accident back in 2017 in Michigan, I think you're spot on. And here's what they learned in that accident investigation. There's the aircraft after this accident. Look at that. His buckets are still out. During this accident, same sort of deal. The captain or the pilot went to rotate the aircraft. Nothing happened. Forced him into a late reject after V1, forcing him off the end of the runway. And what they found in this particular accident was the geared tab linkage was damaged to the aircraft, effectively jamming the elevator. They conducted testing on this aircraft and were able to repeat these results in testing. And here's what these damaged links looked like. One of these is from the test aircraft, and one of these, I believe, is from the actual aircraft. But the test was able to very closely replicate the damage to the elevator from the accident aircraft. And these elevators were damaged. This linkage was damaged by a high wind event where winds exceeded the original design limitations for the viscous dampers on the DC-9. Now let's watch this real interesting, crude but effective test that they did on a sample elevator of a DC-9 following that previous accident. They've got a bunch of weights hanging off the trailing edge of the elevator, it looks like, and they're holding it all up with a forklift, and they're going to cut the rope and then let the let the elevator bang down, simulating wind banging these control surfaces around. First, they're going to do it at a simulated 55 knots of wind gust, which is within the viscous damper parameters of the DC-9, and show you how it's supposed to work.
3, 2, 1.
Bang! Okay, now we're going to look at the link view and this will show you how it's supposed to work. This is looking at the leading edge. This is looking at the linkage for the control tab. Okay, hold that right there. Here's the elevator. Here's the horizontal stabilizer. Here's the geared tab linkage. You see how it remains in a under-centered condition right now? The viscous damper worked correctly, and it stopped the movement of the elevator, and it prevented this linkage from going over center or damaging this linkage. Now let's crank up the load test to beyond the limits of the viscous dampers, controlled lock dampers. Here it is, 60 knots. More weight. Bam! It's down and stays down, it looks like. Now let's look at the linkage view at 60 knots. Again, here's the leading edge of the... Bam! You see that? This thing busted out. I heard something else fall down as well, but this busted out into an over-centered condition for the geared tab actuating servo arm, and so that the thing's over-centered, it can no longer move. It's jammed. And that's what can happen on a DC-9 if you get excessive wind gusts banging the elevator around while it's sitting at the airport. So this is what investigators are going to be looking at very closely, this or something similar to this. Now, if you go and put a flight load on this in this condition, this is what may happen. With the link in over-center condition, if you try to jam that elevator back into position, like with a flight load, you could very well just bend the linkage itself. So it'll be very interesting to see what investigators find with the linkage of the elevator control tabs on the accident aircraft that crashed on takeoff out of Houston, Texas. As a result of this 2017 accident in Michigan, the following post-accident corrective actions were made or recommended. As a result of the load test results, which showed that wind gusts below the DC-9's design limit could, in some cases, produce dynamic effects sufficient to jam the elevator system, Boeing developed a modification involving the addition of a secondary mechanical stop to the DC-9 elevator system, which would physically prevent the elevator from moving far enough past its limit to allow the geared tab linkages to become locked in an over-center configuration. So sounds like they effectively limited the travel of the elevator. For DC-9s with tab-driven elevators not yet equipped with the secondary elevator stop, encompassing all unmodified classic DC-9s, MD-80s, and 717s, the maintenance manual was revised to decrease the wind strengths, which would necessitate a physical inspection of the elevator system before further flight. The NTSB recommended that Boeing finalize and fully implement these changes and also develop a means for DC-9 flight crews to detect an elevator jam before attempting a takeoff. I'm not sure if that was ever implemented or not. So it'll be interesting to see if this accident aircraft had these implementations in effect, or did they not know about the fact that you need to inspect your elevator in less winds that the original manual called for as a result of this accident? So I hope this gives you a better understanding of the DC-9 and the flight control systems of the DC-9 MD-80 series of aircraft. A little blast from the past there. Thanks so much for your support of this channel, especially over on Patreon that make this content possible. See you here.